Welcome everyone to a breaking news, very important live stream here from our T2 Linux and Hexacode YouTube headquarter. I discovered a real-world AMD Zen 4 speculative execution marginality, aka bug, and I tracked this over the last months and only finally was able to pinpoint it over the weekend, and you cannot believe how much time this kind of things take. In the previous live stream I mentioned that it's quite similar to Matthew Dillon's from Dragonfly, who found a similar execution marginality in Phenom 2 CPUs in 2011 to 2012. And what happened here is that for building our Linux distribution here 24/7, day and night, right, that is T2, I constantly build stuff, right, and I overclock and overvolt in limits and or undervolt the CPU for better boost. And I was observing some illegal instructions, or yeah, usually, I mean, I didn't pay too much attention because usually some segmentation fault here or there are even normal, like normal for a configure test to test something and fail, or fail unintentionally because bugs. And in general stuff was compiling, right? So I always thought, yeah, some memory, some instability, it happened sometimes. So eventually over like 12 months, right, I purchased this on launch day, Ryzen 7950X and Gigabyte Aorus Masters X670E. And what I now found, the last month's closer monitoring this, right, wanting to release all the cross-compiled ISOs, I realized, wait a second, also like obviously BIOS updates and memory testing and stuff, and getting a better like 12 months impression of the system stability. And I wondered, like, memtest doesn't show any errors. In general, like on my daily work, I don't have any errors. Why do I sometimes get illegal instructions, right? And it turns out it only happens for Spark 64 cross compiles. And before you say, but what has Spark to do with it, right? It could be any other real world code, right? It could be Geekbench, it could be Chrome, it could be Firefox. Basically, as you see here, it fails usually at CO, let me just check, C0, C0, E0, C, why do I see O? C0, E0, C0. And so that's certainly not an illegal instruction, right? So what you see here is a disassembly of a binary. And again, so this, although I can trigger it reliably, like 1 year later, way too much time and the whole weekend, and obviously I thought system stability, right? And before you say, but you said undervolting, overclocking, undervolting the CPU, maximizing the performance boost, and overvolting the memory and stuff. And yes, I went as far as over the weekend because the last months I thought, darn, how is it possible like 12 months later AM5 is still not stable? Turns out it is stable. Well, except the CPU bug. It's not the memory thing, because over the weekend I finally said, I need the system like 12 months later, let's get it stable, right? And I dialed the clocks back a little bit, instead of 6,200, 6,000, 5,800. And I was like, dude, why is it still happening, right? Then I run a base clock, still happening. Then I disabled PBO entirely, Precision Boost Overdrive. I disabled all boosting, right? I run the CPU at base clock. I run the CPU lower than base clock, still happens. I run the memory and CPU lower than base clock, still happens. I mean, obviously in the meantime, losing over 30% of performance with disabling all the expo and CPU boost. It still occurs. I start to take a closer look, right? And then I realized I have here actually logs. So this happened with, I can reproduce this with Spark 64. However, so there is an instruction sequence. Unfortunately, given the complexity of the nature of machine code and low level, I have not that distilled why it happens here, right? I can tell you something. So also, I mean, obviously I spent the whole weekend on this, right? Weekend and today. And I even patched the Linux kernel to further diagnose, similar to Matthew Dillon from Dragonfly, for a similar AMD Phenom CPU bug. So I can tell you it usually illegal instructions here, which is a perfectly old-fashioned fine move. Given that probably around 600 instructions, or 500, 600, whatever, it's something in this ballpark, are active in the out of order window with all the speculation on modern CPUs like this AMD Zen 4 It is certainly extremely hard, especially for us not having the microcode and the other inner workings. We can only speculate, right? So given to similar speculative execution vulnerabilities, probably either the micro-opt cache corrupts or is like something is incorrectly updated, right? Maybe the micro-opt cache gets incorrectly validated. Maybe some code is incorrectly or speculatively executed, and I sometimes get this illegal invalid opcode exception, right? So that is, the core issue is random, spurious, invalid opcode exceptions. And obviously, like if you just game a little bit or run Microsoft Office, you don't see this, right? It took me 12 months to distill it, so of course it's a showstopper, right? I personally would call it like similar to the Pentium fdiff bug of correct tables. I would say, I mean, not I would, in general, a CPU, like if you give a CPU valid code, it should execute this reliably, right? And similar to all the other decades of massively out of order and speculative executing CPUs, it is so massively speculative executing that something corrupts there, right? Obviously this instruction is not invalid. C0, E0, C0. Sometimes it is another, right? And also, like, it does not always occur, right? So this CPU is 99.9% executing this code perfectly fine, right? Before you tell me, but René, is this code valid? Yes. I also, so what steps did I proceed here to further narrow this down? I dialed all the overclock, the memory overclocking back. I dialed all the undervolting back. I run the CPU memory at stock. I run it below stock clocks and stuff. It still occurred. Then also I rsynced to, because so naive people would then set up a second system. However, it needs to be exactly the identical binaries, right? So if I would run any other Linux distribution or whatever, there could always be like this kernel, this patch, whatever. So as a professional, I rsynced all this state from this 7950X to my 5950X, and the bug does not appear. On the last generation Ryzen 5950X, I can run this all day long, the same, I rsynced it, right? It's exactly the same kernel, it's a bit identical kernel, like not some Windows in some other Windows update state, no. It is the same professional, bit identical Linux system with the same kernel, the same compiler, everything is bit identical, guaranteed by the revolutionary and awesome rsync algorithm. It does not occur on a Ryzen 50X. Then I went even further. So there are two ways I can currently avoid this speculative execution. So again, if you run this, it works, right? You need to run this 1,000 times to trigger that. And you can trigger that, like if you build a whole ISO with our phenomenal, amazing Linux distribution. If I build this all day long, I might get a dozens, right? So I run this in a loop, and you see here, this is so reproducible with just this compilers. And again, take Spark, before you say Spark 64 triggers you, it could happen with any other GCC binary, right? It could happen like you just need the right set of data input of GCC compiled binary. Of course, the GCC compiler binary is slightly different if you compile GCC, or like slightly, it's vastly different actually between x86 and RISC and stuff. But you could, the same code sequence, if I just have not further distilled it down. Somewhere here along those lines, we can also read this. So this is rule function. So as you see here from my notes, it's deterministically every thousandth or so time illegal instruction faulting here in GCC gimpel pass, switch lower, internal compiler error here in tree switch conversion, switch decision tree, balance case nodes, or try switch expansion. Also, actually, the more often occurring is, you see, it's not always this address, right? You see here is one slightly different address that happens only very rarely. Like 99% of the time it is C0, E0. Also, this is the address in my address space, right? If you run this other stuff, it might differ. It's most likely, I mean, it is possible, you never know what's safe in the microcode. However, if you run this at home, of course, this address will differ, right? This is just for this executable, the address. So usually it is in switch decision tree, try switch expansion, you have vector tree switch conversion cluster, the heap and stuff. Very rare, seldomly, it is actually a slightly different address. This is also why I thought it did not really look like a memory problem, but I thought like maybe some cache corruption, whatever, but no. This is slowest clocks, totally downclocked, it still occurs. I have two ways to mitigate this. The first thing, the good news is, this only occurs, this most likely triggers, so I spent some weeks on and off, plus a weekend, so guess how much time went into tracking such complex low-level stuff, right? Share, like, and subscribe, and applaud all the other Matthew, Dylan, Linus Torvalds, and all the other crazy people out there hunting bugs and fixing bugs. This needs to probably best further distilled down, like reducing the test case. I have two good news for you. Either if you boot just the Linux kernel, you will not see this, because at the end of all this research tunnel, I realized booting with mitigations like Linux security mitigations for all the Spectre and Meltdown enabled actually hides this bug, which is probably what many of you run. So also the second part of the title, I've in the last years with all the security mitigations and not really connecting all of our cluster nodes, we need performance, right? So I've actually run all our internal servers and cluster nodes with mitigations equals off for a little bit performance. And most enthusiasts will tell you, you're not connected to, like, you're not running cloud code, whatever, you can run with mitigations off. No, you can't. I now proved, you heard it here first, I found real world code that might be similar or actually trigger the same bugs in the CPU that are also used for all the Spectre, Meltdown, and other side channel security vulnerability mitigations. So that actually, I have to say, 2023, all those excessive work changed my mind. Mitigations equals off considered harmful, right? If you want stable, reliable computational results, no, you can't do this. Because as Spectre, Meltdown, and all the other security issues has proven, the CPUs are nowadays as complex software systems, and when we have already mitigations for, we know they are buggy, and we know security exploits can exploit these vulnerabilities, and we have mitigations for those, you want to use them, even if you are not connected to the internet, even if you do not run untrusted code. This is trusted code. This is GCC compiled. This is open source, totally trusted, open source, compiled from the sources, compiled again and again for 25 years, built on previously trusted sources. This is like 100% plus trusted, and yet it manages to reproducibly fail. While we are talking, just for the illustrational effect, I run here Mesa, building Mesa in a loop, cross-compiling Mesa, and again, this happened for many other packages, right? I have here a list that happened compiling the Linux kernel, that happened compiling Cairo. This basically happened randomly, right? This happened here with Mesa multiple times, near Intel. Basically, the input file doesn't probably matter too much. It probably just needs to be complex enough. And then eventually, if you compile it enough and long enough, it will happen with anything. Here we have, I once had even Go script. Of course, the bigger the package is, like if it's a small package, it compiles with just running the compiler a dozen times. So it's not that likely to run long enough to catch this electrons there. So of course, usually the larger the packages are, the more 1,000 times Mesa, the Linux kernel, runs, the more likely it is. And again, don't let Spark 64 fool you. This is just the one combination that I found by pure chance and luck that is very reproducible, right? It might happen for any other GCC-based compilation, and if we ever, I already started to notify AMD as per usual. Small little YouTuber and software guy tries to contact big mega corporation, nothing happens. So we will see if this ever gets properly handled. It's like, yeah, without a proper research paper. The problem is further distilling it, right? So theoretically, you would need to further reduce this. What I could do is create an initRD with just 100 megabytes with just this GCC-based Spark cross compiler and one pre-processed source file and running it 1,000 times. Of course, testing it on my machine, making sure it actually does fail, and then providing it for you to test and AMD. Similar how Matthew Dillon from Dragonfly BSD did this a decade ago. Like, here's a minimal Dragonfly BSD code snippet thing, and somehow, because like, good luck, I'm really feeling sorry for the AMD engineers who constantly, or Intel for that matter certainly too, who constantly need to debug, like good luck debugging this monster of a CPU and similar microcode, right? Theoretically, in my opinion, well, not theoretically and not in my opinion, I think, as I mentioned 10 minutes ago, if you give a CPU valid code, it should execute this deterministically correctly. So I said already the first good news, mitigations equals on, mitigate that too, but I would actually argue that even with mitigations offer performance, I would expect regular code to run error-free and not like, sure, if you have code that is violently hammering side channel attacks, sure, that is what the mitigations are for. But if you run regular, good old-fashioned normal code, it probably should run, in my opinion, error-free. Anyway, the second thing I found is if you disable SMT, that also apparently work around that. So your mileage may vary for this. For this case, you can disable SMT, simultaneously multi-threading. So that would further indicate apparently some simultaneously multi-threading is corrupting some kind of state, and whatever bits are mixed there or shuffled around or randomly clobbered for this to fail. As you see here while we talk, each time this builds, it builds to some other file, right? Once it fails after 28 seconds compiling. So this is always compiling. This is one system continuously compiling the same sources, and it constantly fails differently, right? This is the speculative, embarrassingly speculative executing bug triggered by this code here. Again, C0, I had this reloaded C0, E0, C0, C0, E0, C, don't tell me I scrolled over it now. C0, illustration purposes, only here, somehow move. Again, before you say, but it only affects GCC, no. This is totally regular, normal C and C++ code, so I would expect any other Firefox, Chromium, Acrobat, Windows, Edge, whatever, any other code could potentially trigger that. It's just the right set of memory access, cache access, and function call and return, so whatever is needed to corrupt this processor state. And again, this is not a exploit explicitly triggering executive speculative execution and side channel marginalities. This is just regular compiler user. This is not even very system I/O intensive user code. It's just reading some stuff, generating some memory structures, writing some result to disk. So that is all GCC is doing, right? And it can absolutely not do that. Like it's not happening once an hour. Like if you have the right set of conditions, it's constantly happening. I can trigger that every 30 seconds on average, right? It's absolutely crazy. So 2023, I changed my mind. Mitigations equals of considered harmful if you want your computer to work reliable. Theoretically, I would need to probably further work on this. Maybe I try to create an ISO, like a 128 megabyte test ISO for you to test, and AMD, I wonder what AMD will say when my contacts ever answer, and it's like they want to test this. If they say, mitigations off, it's invalid, only mitigations on, I could. So further stuff, reducing this test case further. I mean, I could easily take one GCC executable, one preprocessed file, see if it reproduces, runs this in a loop, and puts this into an initRD, and like have 100 megabyte initRD with just the compiler, just the file, and probably trigger that easily. Fingers crossed, hopefully. Reducing this further, like good luck, that's certainly a research project for whole summer. Like reducing this whole test case further, thank you very much. But yeah, in the meantime, between now and forever, probably mitigations on from now on until the next speculative execution and side channel marginality. And was there anything else to be said to that? Yeah, leave in the comments below. Should we further work on this? But this also like IT security standing on the shoulders of 10,000s of people worldwide who constantly find those issues, like basically field engineers finding, discovering, debugging, like having the nerves over months and weekends to distill, actually finding out like what the heck is going on here, like this is going on. I can actually, so as you see, I'm not even sure we can kill that, oops. Oh, this is why. We can reboot with illustration purposes here, and then I go to the comments. So this is how often this occurred. Also, so this is not an upstream proper. So another win-win is I now have a patch, a few liner, like because by default the Linux kernel is not printing this information. I patched that in. I did this morning because over the weekend I didn't. This complexity line. Initially I thought it's surely DDR5 instability. No, it wasn't. Then I thought, is my AMD CPU defective? Although I undervolted it, I nicely cooled it. It surely shouldn't, like it's running in AMD's thermal envelope. Is this just my CPU? Do I need to go out buy a second CPU? Because of all the ARM, UltraSpark and RISC-V stuff, SJ Octane and UltraSpark, I don't even have a second AM5 CPU because I'm not such a hoarder. I'm a collector of nice stuff. I'm not like hoarding AMD CPUs. So then I thought, like, is my CPU defective? This is the thought process, right? That takes, like, you think about Zen. Then I thought, like, is it overheating? I didn't know, like, because I patched this in, I wasn't sure, like, or I had no information from the operating system which threads and cores it is, right? This is why I patched this in. I wanted to see, is this deterministically only one core? Or is it more? Do I have, I grabbed and sorted that actually. I probably don't have that here anymore. I actually grabbed, you can grab, I sorted this. You already see this is happening on all cores. Because I thought, like, is it just one core that is the manufacturing process is lithography? Was there some? Is there some defect in some logic gates and some transistors, whatever? But no, it's all of them. So I'm basically 99% convinced it's not my CPU. It's defective. because this is not only too reproducible, it also disappears with mitigations and SMT disablement, and it happens on all cores, right? If it would have overheated, which I'm pretty sure it didn't, because I undervolted it massively. If this CPU would be defective, I would think it should only occur on one core, and not on all. And as you see, it occurs on all cores, right? And that is the sort of process, right? Overclocking, DDR5 long-term stability, manufacturing defects, and so on. And at the end, embarrassingly, Kofefe, specular mis-execution, marginality. So let's boot with, let's reboot with mitigations off, mitigations on. So that goes away here. AMD. Also, I thought then, is it MDP state? I also thought, is it then is it because I booted with ACPU enforce resource stuff here lags. By the way, let's re-enable that. I need this unfortunately for, and that is the thing, right? You have, even if I would not have these options, they would still be there, right? It could always be like, is it that kernel feature? Is it a kernel bug, right? It could also be that it's some memory corruption in the Linux kernel. It could basically be everything, right? Prev core, it's like 2023, you need to boot with all the stuff for all the good stuff. ACP enforce resource Lex is this, and this is not the right kernel. We want to boot this one here, and then I tested at least one kernel, right? Because I wasn't sure, like, could it be kernel bug? At least I tested one more kernel, adjusted it, freshly installed. Theoretically, I always have many more old kernels. It's just that right now this is a fresh installation. Otherwise, I would have had here a dozen kernels of all the previous updates. But yeah, that is the thought process behind this, the long hunt for CPU marginalities, bugs and features. Shut down, let's hope this reboots. While we take a look at the comments and answer some questions, can you try to reproduce this on some other Linux distribution? I could if I would put more time in there, but I have zero. We patch quite some stuff, but given that it disappears with SMT off or mitigations on, I have no reason to believe. Actually, I considered this, right? If it would not have magically disappeared with mitigations on or SMT off, I would have next loaded some Fedora or whatever they are named currently, just to test, but the likelihood is, in my opinion, next to zero. To make sure it's not on my very particular setup, thanks for the suggestion. I think given that mitigations and SMT off, I also, by the way, then obviously even with the base clock, today I swapped out the memory with my two kits, which is also why I kept it. Like I'm not hoarding CPUs. I only have one AM5 CPU, but I kept the memory because this was my original kit, right? Previous video, 64 at the time, a year ago, largest kit, and then I need more memory. 96 gigs of memory. Yes, I tested another memory kit today too. It wasn't a memory kit. I think with mitigations off, it is proof enough that let's see if that is mitigations safe. Read no microcode. What here? A lot other stuff not affected. The old stuff, speculative store bypass disabled via PR control, user copy barriers. I mean, maybe it's some user copy barriers or sanitization. Next, I could also go through all the mitigations and disable one by one. Enhanced automatic IBRS. The thing is, there are so many mitigations. I mean, where do you want to start, right? But thankfully, I now have a very good reproducible case. Let's see. So that should have been resume AMD core P state and resources. Do we remember SPD 50 218? Of course not. I currently can't remember my own Linux kernel driver. Also need to upstream at 5118 apparently. This is why I need the ACPI resource like stuff to have the I2C bus driver here to see my memory temperature. Anyway, as you've seen live here on this video, previously before I rebooted with mitigations on, it did not compile once, right? It usually failed around 30 seconds, 28 seconds, 26 seconds, 30 seconds. It built. First try, 47 seconds. The only change, well, the only two changes ACPI resource lags, but the main thing, trust me, I tested this. I should have only enabled one, but I didn't want to reboot again. But yeah, mitigations on. You heard it here first. Mitigations off, considered harmful. Don't do that at home anymore if you don't want to waste your time like I. I hope you enjoyed this, learned something. So we're building this in a loop, so most likely while we talk it will finish a couple of more times just to prove the point. Could it be that mitigations off is just buggy on Linux? Yes, it is possible. However, I've run this mitigations off for a year and all my other builds do not exhibit this behavior, right? So in my opinion, given that I would say, because I had extremely intense workloads, right? And if mitigations off would in general be, but also no, because I run the same kernel on the Ryzen 5950X, right? Which is also crazy, right? The old Ryzen, different speculative marginalities. So I would say no, it's probably not in general buggy because the build passed with mitigations off on my Ryzen 3950X. And I think I had double checked that I had this booted with the same environment. But let's just double check that yeah, mitigations off. I usually, yeah, this is also running 1550X. Here. 5950X mitigations off. This is how I usually have run everything to squeeze a little bit performance. But I need to change that now. As you see, this is not a fluke, right? While I was live streaming this video, dozens of builds failed, and since I rebooted with mitigations on, the builds pass. Exactly the same compiler. I changed nothing, right? I did this for 48 hours, the whole weekend. Nothing else changed, nothing else matters. But I will probably theoretically, I'm curious if I get anyone from AMD to respond, which theoretically they should, right? That's also the thing, right? 2023, you need personal contacts in the industry, because if you, like, how do you officially report this? On the website, product support, forum, email forum, hey, like, hey, a processor RMA or technical support thing, like, hey, I found a CPU bug. Here is some stuff. It's like, what are even the procedures? Basically, I would say with all the official procedures, you will for months and years not reach the right people. So you need to social engineer network and have friends and family everywhere to actually have this escalated enough. And also then on top of spending all the research of finding out what's actually going on here, you need to spend even more time of social engineering and network building to know the best people at, like, 2023 as a low-level kernel programmer. You need to know the best people at Intel, AMD, NVIDIA, ARM, Apple, or whatnot stuff. It is absolutely crazy. As crazy as it is that we're still waiting for the AMD microcode update. What even was the last, or AMD security, what was the last one of Inception, right? We don't even have a security mitigation for, is it this one? Probably this one. we don't, the craziest thing is, and I criticized this before, as much as I otherwise I was quite an AMD fan, right? One of those mitigations we don't even have, like this, we don't have mitigated for months, and the promised fix, I said this months ago, it is totally what is the best way? It's not serious, it's unresponsive, totally unresponsible that they want to mitigate this by December. In the meantime, we are December. Was it this one? Some of this, was it this one referred to, or is it the other? There's so many, one of those mitigations, what was the other? How do they call this, consumer? Because one of those mitigations is only promised for, oh, best without typo. Is it this one? This is Zen 2. Ah, whatever. There was one where they promised this. What was the freaking other? Ah. Is it Zenbleed? Maybe it was Zenbleed. There are so many names. I need my own table to. Yeah, not even like counting this because, yeah, or is it, like how many do we even have here? Client one is like, ah. Anyway, we're basically through. That's it for this video. Also, last but not least, I would say, this is why I love RISC-V, and we're still building, right? As Intel and AMD both prove, x86 surely the monster they created is surely way too complex to implement in any way, shape or stable form. And proven again and again, over and over again, from Spectrum Meltdown, other side channel attacks, and this totally fine. User code here doing its thing. And I'd rather have very reduced, like there is a reason why the big mega corporations came up with RISC in the 90s. MIPS, Spark, PowerPC, ARM or others, and or 80s and 90s, and they should dominate the world with high performance computing today, because the complexities of 600 very complex instructions in flight in modern reorder Windows in modern out of order speculative executing CPUs is surely way too large and way too complex for humans and machine verification to handle. That's probably all for it today. Question, do I still use T2? If you mean T2 or Linux, then of course, or do I not have, oh, did even emerge that? Of course I do, I'm live streaming from it. I'm literally sitting on my T2 thin client Steam Deck desktop and my Ryzen 7950X. Like I'm sitting between my two build servers, 7950X and the Steam Deck. Of course, all things are T2 here, from ARM to RISC-V over Ultra Spark and MIP64. You can try serializing some instructions around the buggy location with full barriers in a way where we verify something is wrong on the CPU. Yeah, so the promise is this is of course building in GCC, so either you would need to dissect this with ELF tools. It's of course non-trivial, right? You would either keep the GCC build and then use the compiler output and inject assembly there and other such trickery, or either binary. Even probably I would try the pre-processed assembly source modification first. Yeah, you could, yeah, we and AMD share, like, subscribe, Patreon, GoFundMe, YouTube membership, super thank and whatnot, because obviously after spending so much time, sure, the time, the attention to detail, the hours necessary to further work on this are surely endless. And what else do we have here? Microarchitecture. Is there something to do with internal FIFO, since the bug occurrence is totally random? It feels the bug is not totally random. I would not call this totally random. As we rebooted, so we currently don't have this printout here. Do we still have that in? I Control C that, right? But we can simply go. I can show you this again. It's not random. It's very precisely triggered by just this code. The $1 million AMD product support question is only which precise sequence of instructions is triggering that. This was C0. I can also show you the other though. So this is the other. So this is C08 AAF 8. AAF is also a move. So at least both of them. Oh, there's also my OBS thing now. There's my OBS thing. So what they have and what both locations have in common, that this is a move. So, but the question is, that was C08 C08AAF, right? So jump equal, so it must have run move inc, so and then move 18 hex R8 R9 EDI. So, but the thing is, due to 600-ish instructions in flight in the reorder buffer and stuff, it could way be before, right? It could be dozens of instructions before causing corruption and this illegal instruction. So the more, like 99% of the time it occurs at C0E C0 C0E C0, or it's C0E C0. It's also a move difference. So this is move R. I mean, it's not that much. Whatever. So it clearly must be something. So I mean, maybe you could potentially. I mean, maybe you could use a reverse debugger to capture. But this reverse debugger is also not 100% super stable on AMD. The question is then, if you disable the features needed to run the efficient reverse debugger here, maybe the bug goes away. I mean, maybe that would give you some more trace of instruction stream needed to trigger that. But I mean, yeah, one could try that. Do they have a new release, by the way? Do we have a win-win of 5, 6? 1 year no release? Come on, folks. You can do it. Anyway, one last question and then we call it live stream. Overpaid managers of big tech. Everything's automatic and press on the button. Thanks for the wishes. I hope you enjoyed to learn something. Recurring reminder. Mitigations equals off from now on here, considered harmful. Don't try this at home if you want stable and reliable computational results. As you like, it not once failed, right? Previously it was deterministically failing, now it's deterministically succeeding. And I'm currently running back with full overclock, memory, like CPU undervolted, memory a little bit overvolted and heavily overclocked, 6200. I run this as finely dialed in as ever, and it's rock solid, right? I should test one thing though. I should actually test the performance and how much performance we lose. So that would be x86. I usually know the performance of x86 Linux kernel and Firefox. I mean, yeah, I could actually try Firefox first. That's it for today. I hope you enjoyed to learn something. As always, would mean a thing if you share, like, subscribe. And I hope to see you soon for all the next fun and similar low-level stuff to come.